All right, so I'm just gonna start off very slow by introducing myself while everybody else joins, so I'm not wasting your time. My name is Mohammed Sada. I work at the University of California at San Diego at the San Diego Supercomputer Center, and I mainly work on the National Research Platform and the Kubernetes cluster we run, which is called Nautilus. And today I'm gonna be giving you a brief tutorial about ESnet SmartNIC. And I know this is a topic that many folks and many groups are very interested in. So, and 1 hour just doesn't do it just, and there's plenty of things to go over. So we're gonna try to go over as much as we can in the next hour without it being overwhelming. And in case that we need more time, I'm always more than happy to have this become a series instead of a one-time thing, and we can dive deeper into more topics and into more use cases and how to use it and so on and so forth. But for now, in the scope of this Zoom session, I'm hoping I can introduce everybody to what ESnet SmartNIC is and how to use it in the context of environments that provide official support to it and access to FPGAs that it can be used on. And by official support, I mean here that like you go off, you try to reproduce anything breaks. I mean environments where we can actually go in and help you one-on-one and directly in the issues that you might face. And I'm just gonna go start off by talking a little bit about the National Research Platform for whoever is not very familiar with what NRP is. So basically, in simple terms, NRP is a partnership between academic institutes. It's mainly led by researchers and staff at UCSD and UNL and MGH-PCC. And the goal of this partnership is to sort of pool resources and collaborations and contributions from different federal agencies like the NSF and the DOE and ESnet and the DoD and so on and so forth, and between academic institutes in providing one large Kubernetes cluster that at this point it's an international cluster because it spans across 3 continents, and we're adding more nodes every single day. So for example, this slide, whenever I update the slide, it's always bigger and bigger numbers. Right now we're at 1,468 GPUs, for example, in terms of resources. We have hundreds of research groups, and we try to provide a variety of resources as much as we can in terms of having CPU compute nodes, we're having GPU nodes, and having other resources as well, such as programmable network components, FPGAs, other cutting edge accelerators. For example, we just added the Qualcomm Cloud AI 100 Ultra cards. Those are AI acceleration cards. They're very efficient when it comes to running LLMs and fine-tuning LLMs, as they're more capable than GPUs and they consume much less energy. And our goal here is to provide users with an environment that not only provides the hardware resources, but also provides the software environment that accompanies them, especially for research groups and researchers. We aspire to provide a sort of plug and play environment where you have everything. You have your support system, you have your documentation and everything where you can just hit the ground running instead of wasting the bulk of your time in getting up and running. And this is what we hope that we provide here with FPGAs. And I'm going to talk about the FPGAs that we provide on the National Research Platform and the Nautilus cluster. So NRP has 32 of the Xilinx Alveo U55C FPGAs. And I'm just going to talk a little bit for folks who are not very familiar with FPGAs, especially folks, for example, who are coming from a networking background and not very familiar with FPGAs. So FPGA is short for Field Programmable Gate Array. And field programmable, that as the name entails, it means it can be programmed in the field, as in it can be reprogrammed after it's been deployed, after it's sitting on the server. It's fully programmable hardware. So whoever is programming the FPGA can reprogram it from scratch on the hardware design level to be very highly optimized to do the sort of task that users want it to do. And gate array is, of course, an array of logic gates, which means on the hardware level, it's programmable to the wire level. And this is sort of an analogy you can think of here, but you can think of a CPU or a GPU as a Swiss Army knife that is fit for everything, but does all kinds of tasks, but it's not optimized for a specific set of tasks that it does at a very high throughput and low latency. On the other hand, FPGAs are like heavy machinery, and they're programmable heavy machinery and reprogrammable heavy machinery. That means whoever is using them and programming them can use them to do their task. And this is what we're going to be talking today about, which is using those FPGAs as SmartNICs, the Alveo U55C FPGAs. And for network engineers who want to use them as SmartNICs, and SmartNIC is short for Smart Network Interface Card, which is a network interface card that does all sorts of advanced functions that can be offloaded. You're either offloading network functions from the host, so the CPU and the host node doesn't have to worry about providing
Hello?
tasks and can be freed for
Hi,
everything.
this is Matt. Well, have you heard it?
Sorry, there's
Hello?
Hello, can you hear me?
Yes?
sorry.
This is Matt from Empower Solar. I'm just calling because we had some designs drafted up for you for a home
So
solar.
Jess, can you mute? Thank you.
Oh, sorry about that. So to carry on, so the Xilinx Alveo U55C FPGAs, for network engineers, when they're programmed as smart network interface cards, that means they can offload functions from the host and the host CPU. They can also offload functions from the network switch, and those smart network components can be pushed off to the edge onto the FPGAs, which interchangeably here we call them FPGAs or SmartNICs because we're talking in the context of using them as SmartNICs. And of course, those FPGAs, essentially what we're talking about here is, sorry, let me show you the picture. They're PCIe cards that sit on the Kubernetes nodes. So they sit on servers and on hosts. And through the PCI bus, they can talk to the host system. And each one of these cards has two of a 100 gigabit per second ports. And these ports, we conveniently call them Ethernet ports, but as we mentioned, FPGAs are very highly programmable, so it doesn't even have to be Ethernet. You're specifying your packet processing logic from scratch, from the ground up, however you see fit, however you want to use. And typically, the U55C FPGAs consume 115 watts of energy, and one of the perks of using them is that they have high bandwidth memory. Each one of these cards has 16 gigabytes of high HBM2 memory at a bandwidth of 460 gigabytes per second. And like we said, we have 32 of these cards. They're situated in the sorry, I switched the slides. They're situated at the San Diego Supercomputer Center at the what we call the PNRP nodes. Each node has 2 to 4 FPGAs, and all of those FPGAs are also behind the P4-programmable Tofino switches. So you have programmability on the switch side, and that is one aspect that we're working on providing for the cluster users, for whoever is using Nautilus, so that they can have pipelines where they can program on the switch level and program their network components on the switch level and on the FPGA level. But for the sake of our talk today, here we're going to be just strictly talking about FPGAs. And in general, their use cases are not strictly for networking. Many folks use them for science research, and we've had use cases of users on the cluster using them for metagenomics research and processing acceleration for genomic sequencing, aligning and trimming, and so on, and other tasks. And we've had folks using them for machine learning and AI acceleration as well, especially the HLS for ML folks. They use the FPGAs to provide a pipeline where you can plug your PyTorch model and it'll do all the steps for synthesis and loading on the FPGA and offloading all that, offloading inference tasks onto the FPGAs. The interesting thing here to mention is that this approach uses the PCI bus with programming them as SmartNICs and using them for network functions. You actually make use of the PCI bus and the 2 by 100 gigabit per second ports. So with programming them with P4, you have four ingress and egress ports for the network packets, which are the 2 ports that actually go to the network and 2 logical ports to the host itself. So you can run, for example, applications like DPDK, which is short for the Data Plane Development Kit, and it allows you to run network applications and network functions by bypassing the kernel and achieving high throughput in the user space. And by having those 2 channels, you can send packets to the PCI bus and process packets on the host as well, not purely on the FPGA also. And this is where ESnet SmartNIC comes in. So ESnet SmartNIC, basic what it is actually. So it is a software framework. It is a set of repositories that are provided to users, and they're all publicly provided on GitHub. So anybody can go on GitHub on github.com/ESnet, and in their repositories, you'll see four repositories that are relevant to the ESnet SmartNIC project. Or does anybody have a question?
Sorry, no.
No, you're good. So it is a set of repositories that together provide a framework for using the Xilinx Alveo cards, including multiple models like the U280 FPGAs that are, for example, available on the Fabric testbed for those of you who use the Fabric testbed, and older cards as well, like the U200 and so on and so forth, and the U55Cs that we're talking about here today. And essentially, what it acts as, it's essentially a set of tools that operates on top of the open NIC shell provided by AMD that allows these FPGAs to act as SmartNICs. And by using the set of tools, you have easy access to all sort of software tools that we're going to see, like probe counters and easy an easy way to launch a containerized DPDK and packet gen without having to go through headaches to get DPDK up and running. Because if it's painful for regular NICs on one level, it's much more painful to get DPDK up and running for advanced hardware like FPGAs, for example. And it comes with all sorts of testing tools, behavioral simulation tools and automations, PCAP files for testing, and so on and so forth, especially when it comes to testing for control plane and table entries, which is what we're going to be seeing here today and what we're going to be talking about. And of course, in talking about the ESnet framework, before I go on to the hands-on section, we have to it's easier for us if we differentiate between a development environment and a deployment environment. So the development environment is the one where I'm writing my P4 logic. And for those of you who don't know what P4 is a packet processing C style language. So it's very easy. It's simple. In syntax, it's very similar to C and C++, but it's very simple to write, very easy to write. We're going to be walking through a brief example, and you can define your packet processing logic inside of your P4. And your development environment is where you write your P4, you test it against packet trace files and other test cases, and where you build it and build the artifacts. When but what we mean by artifacts is the set of files that we're going to be using to load it's the set of files that are compiled into an archive that is used to load the logic onto the FPGA, and the compiled bit stream is part of the artifacts. And then you have your deployment environment, the one where you actually load the logic onto the FPGAs and use all sorts of tools and deploy them either for testing or for deploying on the actual network. And the differentiation here is the development environment needs special software like Vivado, for example, and special licensing, which we provide, and we're going to talk about how to use for all cluster users and all users who are interested in using Vivado. And the deployment environment relies on having the FPGAs available, so they do not have to be the same environment. And I'm just gonna pause real quick here for a minute and ask if anybody has any questions up to this point. I don't want to be brushing over stuff very quickly. Before we start with the hands-on section, while everybody gets a chance to get the link and check out the repository, I'm just gonna pause here for a minute and ask, does anybody have any questions? Great. If you have any questions, feel free to send them in chat. Let me check the chat to see if there's anything. Yeah, so John, I'm just gonna make you co-host in case anybody in case anybody needs to be unmuted,
Okay.
do so. And Geronimo, so for U45N cards, uh, more information about this can actually be also added by Chris Neely from AMD, who's generously joining us today on the call. But U45N are also Alveo cards, and they support the Open NIC shell, and we're constantly working with Chris on deploying Open NIC shell on the U45 N cards and or the SN1000 cards. We use the names interchangeably because as it's been explained to us, it's a rebranding. But so far in our personal experience in deploying them, we're still running into some issues with deploying OpenNIC shell, with establishing a link, and having it up and ready for users without any points of friction or pain points. And for Anthony, you're asking, is there a difference between the use of FPGAs and ASICs? So the main difference here is that ASICs, for example, for Tofino switches, ASICs in general are programmable hardware, but for a specific set of tasks. On the other hand, FPGAs are very general and can be used for all sorts of use cases and tasks. So when you're comparing, for example, Tofino ASICs to P4 SmartNIC FPGAs, there's similarity here, but on the other hand, there's no such thing as this is only a SmartNIC FPGA that is only for P4. It's fully programmable hardware. You can program it to do whatever and optimize it to do whatever task you want. So when we talked about folks using them for metagenomics and for other use cases and AI and ML, they're the exact same cards. It can be reflashed and reprogrammed to do different tasks that utilize different resources on the cards in different fashions and using different IPs. You're welcome. All right, I think we have the link here. So it's github.com/nrp-nautilus/ESnet-SmartNIC. Let me find the repository.
I put the link in chat.
Yep. Thank you, John. So we're going to be working, these are the exact same slides I showed you, and these are the 3 notebooks we're going to be working with and showing you a quick demonstration of. So the environment we're going to be running those Jupyter notebooks in is called Coder, and you can access Coder by visiting coder.nrp-nautilus.io. And from there, so you'll see templates if you visit templates. And right now, temporarily, we have signups disabled. So, John, can you please help me if someone needs access? Can you please help me with providing them with access?
Sure.
Thank you. I appreciate it. So if you go to coder.nrp-knowledge.io, normally you can just log in using your single sign-on, using your campus SSO or your federated identity with CI logon, and you'll see an interface that looks like this. And basically what this provides is a GUI that allows you to use the Kubernetes cluster without having to know Kubernetes and without having to write YAMLs, without having to sort of reinvent the wheel. We provide you with templates that allow you to do all sorts of workflows. So you have a CUDA PyTorch TensorFlow image. If you create a workspace using this template, essentially what you're doing is creating a pod. So it's a Kubernetes pod. It's a single unit that runs a Docker container. And that Docker container is ephemeral in nature, but when you create a workspace, a persistent volume is attached to it on your home directory. So whenever your Docker container stops, all of your information, all of your data inside of your home directory are preserved in the persistent volume. Similarly, we have the U55C FPGA Vitis workflow. Using this one, for example, comes with your Vivado and Vitis tools already pre-mounted to /tools/Xilinx. And the license server, for example, is already pointed to as an environment variable for whoever uses this template. Similarly, all of these templates also have persistent volume claims to your home directory. You can use it directly. And sorry, this is about signups. And we have different templates. The Docker template, for example, allows you to use Docker within your Docker container that is running on your pod. So the actual Docker command. This comes in handy when there's cases where you're using Docker Compose, which is our case here. We are going to be using Docker Compose in the ESnet SmartNIC tools, because the ESnet SmartNIC tools, essentially what they boil down to is Docker containers. So you need your pod to be able to launch Coder, and this is one use case for why we use Coder, is because it provides access to Sysbox, which is a tool that allows us to run rootless Docker without having users have too much privilege in the pods that they're running from the host they're running on, the host node, so the actual server. This is the one we're interested in, the ESnet FPGA SmartNICs template. And when you create a workspace, you just have to name it, and you can For me, because on the admin side, you can specify who owns it, but for you, it's going to be defaulted to you owning it. CPU cores, how many CPU cores you want to reserve for your pod, how much memory you want to request, and which node you're landing on. So right now we're limiting our ESnet SmartNIC pod nodes onto to these four nodes, which are node -2 -6 -7 -8 and -11. Each one of these nodes has two Alveo U55C FPGAs. Those are the ones that currently are now available for users to use for their experiments for ESnet SmartNIC. We have more nodes with FPGAs. There's -9 and -10. Both of those have FPGAs, but if, in terms of full disclosure, we're using those for our experiments. So for users to run their experiments, we have those four nodes. And the rest of the 32 Xilinx Alveo U55C FPGAs, the rest of those are flashed with the XRT shell, which is the Xilinx runtime shell, which allows users to write HLS applications and you write applications for them using C++ and Verilog and VHDL and so on and so forth, and use them. Of course, the FPGAs are not by design specified for one path or the other. They can always be reflashed for one purpose or the other. But the distinction in us having them, I think the split is 20 for XRT and 12 for Open NIC shell, is that for whoever wants to use them as SmartNICs, there is no need for reboots and power cycles. Uh, Users can just run their experiments without having to reboot the entire node, because the entire node is serving different resources to the cluster, not just the FPGAs, including CPU and memory and so on. And on some nodes also GPUs. So I already started my workspace that I'm going to be doing the tutorial in on node -2 -11. And you can see this is what a started workspace looks like. I know I'm talking about, I'm sort of getting away from the point here, but just for users who are interested in using Coder and for their work on the cluster. And of course, everybody's welcome to use the cluster for their research and for whatever projects they're working on. And Coder is one main way to use the cluster. Another way is using Jupyter Hub. We also have a public Jupyter Hub. Just gonna send it to you. Jupyter Hub. Also, like everything on the cluster, it uses single sign-on and federated identity. And of course, we try to encourage FPGA users to use Coder just purely to get the features that we're providing. Because, for example, your workspace will get Jupyter Lab. When you click on it, it's going to open in a browser window. This is Jupyter Lab running directly from the pod itself. So from the Docker container that has the OS, this is running from it. You have a NoVNC desktop as well for folks who are going to be using the FPGAs in different ways. Having a desktop environment is very convenient to actually have Vivado and Vitis with a graphical user interface. And VS Code Desktop, we have this is Code Dash Server is running from the pod itself, so it also runs in a browser window. You have VS Code running from the pod, and there's VS Code Desktop integration, so it integrates with your local VS Code. So please check out Coder. There's plenty of use cases. And if you go on our docs, so our documentation is docs.nrp.ai.
I just added everybody that's requested, I believe. Go ahead and give it a try. You want to use the OpenID Connect?
Oh yeah, sorry. Sorry, this is I sent in the wrong link. This is our public Jupyter Hub for whoever wants to use it. And thank you, John, for all your help on getting users access to Coder. So this is Jupyter Hub. Oh, sorry. Let me remember what I wanted to do. So this is the link to our documentation. And we added this tutorial today here. It's in our documentation and the repository. So in case we run short of time, you can always try to reproduce it on your own. If you run into any issues, we can always work together on them. In our docs, you can see links to joining our matrix. So we use matrix on the National Research Platform as our main way of communicating. So we use matrix chat. We have in our docs, if you search for matrix, you'll find steps on how to join. And if you go on Element is a matrix client. If you go on element.nrp-knowledge.io, you can join our chats, our Nautilus support chat, our different channels, and you can chat with everybody, including the operations and admin teams, and we can help you with whatever issues you run into. And the other thing I wanted to mention was yeah, so you have your matrix chat, you have access to docs, and I think we're good to go. This is our Jupyter hub. As you can see, you should have your Bash notebook kernel available. So we're going to be using Bash in our notebooks, not Python, because we're going to be running commands directly on the node. And the first step is for us all to clone the repository. And so one thing to note here is doesn't matter what node doesn't matter what the node you're running on until it comes to actually running on the FPGAs, because all the software stuff can be carried out on whatever node you want, as long as you're using the ESnet, the SmartNIC template, or the U55C FPGA Vitis workspace template. Both of these have the Xilinx tools, mainly Vivado and Vitis, that we provide, and we're going to be needing Vivado and the license server to carry out the experiments. But technically, you can use any node on NRP. And I'm just going to start off with the first notebook that shows us the development environment and how to run, write, and test the P4 program behaviorally. So you're testing it against packet trace files, against PCAP files, and you're exploring the environment. This is before running on FPGAs. And we have our information on what this was tested on and so on and so forth. But there's some stuff I'd like to mention, some technical stuff is that, like we mentioned, the ESnet SmartNIC tool stack is a Docker Compose stack. So whatever environment you're running in needs to be able to run Docker. This is why we use Coder. We use this template which has sysbox, which allows us to run Docker from the nodes. The other thing is, like we mentioned, you need Vivado for development. So this is the development environment where you're writing, compiling, synthesizing, you're doing all of those steps, not when you're running on the actual hardware. You need Vivado, and more importantly, you need access to the proper licensing. So we have an evaluation license from AMD, and this license is in the form of a license server that we have running on the cluster. And for those of you who are familiar with Kubernetes, the server is running as a Kubernetes service called Xilinx D on the Xilinx-dev namespace. So whatever pod is running on the cluster, if you add this environment variable, and you have Vivado, if you check the Vivado license server, which is VLM, if you type in VLM in the terminal, it'll start. If you point to this variable to this location, which is port 2100 on Xilinx-dev, it'll take you to the license server, and we're constantly updating it, so you'll have access to all the licensed IPs you need for SmartNIC use cases. And for flashing the FPGAs, for regularly users in the scope of the tutorial, in the scope of using ESnet SmartNIC, you're not doing anything special or any edge cases. Normally, you don't need to flash the FPGAs, but for flashing the FPGAs, you need JTAGs, and you need a JTAG over USB connection. What that means is that you need an external micro USB cable that runs from the FPGA onto the actual host, and you're running inside a Kubernetes pod, which runs on the node, and we have that USB connection peek through to the user that so they can see it using something called the Smarter Device Manager, which allows us to sort of pass through USB to the actual pod for users. And of course, flashing the FPGAs requires a power cycling of the entire node that the FPGA is on it. So whatever user requires a workflow that needs FPGA flashing, please coordinate with us. We'll be happy to accommodate you. But in terms of flashing and rebooting, sometimes we might say use this node as opposed to this node, and it might need scheduling for example, downtime and power cycling the node. And in terms of FPGA availability, like we said, we have 32 of those U55C FPGAs that we're talking about. We also have, if I recall correctly, we have three Xilinx Alveo SN1022, which are the U45N FPGAs. And we recently added 16 Bitware 520 and MX Stratix FPGAs. And they're going to be available for users to be provisioned in Coder in a very similar fashion very soon. And And another thing to mention, and this is more Kubernetes related, is that you're programming these cards to be SmartNICs. And in plenty of cases, you're going to be exposing them as network interfaces on the OS, on the pod. And to be able to do anything with those interfaces that requires a network operations, for example, something as simple as pinging from the interface, you need explicit capabilities that are on a case-by-case approval generally for cluster users. But for coder users, if you're using the ESnet SmartNIC template, you have those capabilities and you can use those network functions. But normally, if you're running stuff in your own namespace, that is also one thing you have to coordinate with us. Another thing is that DPDK, for example, requires huge pages and requires IOMMU pass-through. And also, we provide those on the nodes that host the FPGAs, and they're properly configured in the definition of the templates. But if you're running things in your own namespace or your own environment, so on bare metal, or on using KVM, or if you're running things, for example, on the Fabric testbed, the Fabric folks provide you with the notebook that shows you how to set up huge pages, for example, and IOMMU pass through inside of your VM on Fabric. But these are things to consider in running your environment. The other thing to consider is that here on Nautilus, running the stack requires an advanced level of privilege, and having that privilege available for your pod, which means having extra capabilities from the pod peek through from the actual node it sits on. That means there's extra space here for users to sort of mess things up. And if normally things are bound to break. If something, let's say, breaks, that is fine. We can always work things out. But having extra privilege means slightly extra space for malicious uses, and for anything malicious, it is immediately caught, it is immediately reported, and their precautions are much, much bigger than what the malicious use is. So I can't stress this enough. Please go through our acceptable use policy if you're going to be using the cluster. And please make sure that your environment is ironclad, you're not sharing credentials, and that you're using the cluster responsibly. And the ESnet SmartNIC framework, as we mentioned, is provided by the ESnet folks and the Department of Energy, and it's open source. And we're going to be working on going through a brief example together here. So the way the set up the notebook is that it cleans up in the beginning, creates the directory, it clones in it. So you can see here I have my ESnet SmartNIC. You can see I'm cloning the repository here. So this is my ESnet-SmartNIC-HW repository. I'm checking out at a specific commit, and that is the way we have things set up. Normally, we test at specific commits that everything works, and we have the versioning for everything matching in commits. Because, like we mentioned before, there's 4 different repositories, and the HW one, which is short for hardware, and this is the main one where you're going to be writing and building your P4 from. And this is where we check out this commit for it. And go ahead, Matt.
You're showing the GitHub screen publicly. Is that what you're trying to show while you're talking through all this?
Are you seeing the notebook or?
No, we've been seeing the GitHub.
Oh, my bad. I've been going on for a while. Let me see what's going on.
Are still people, how many people are able to log in? Why don't you put your hand up on the screen?
All right.
Or who's still having problems?
Do you mean log into Jupyter or
Coder?
Coder.
Sorry, go ahead. Or sorry, you might have been just raising your hand for.
All right.
Can people see the screen now?
Yes.
Yes.
All right, perfect. So far, does anybody have any questions other than coder credentials?
I had one fast question. I noticed the Jupyter Hub it doesn't have an ORCID login. Is that intentional?
Yeah, that is intentional, but is one of the things we're working on. So the way our Jupyter Hub works is that there's sort of a whitelist for institutions that are allowed or identity providers that are allowed. And
Right. CI logon, right? And then it chooses
Yeah.
which external. Right. I remember Orchid used to be one of them, and currently it's not. So I wanted to know if that was a longer term change.
Yeah, but one of the things we're working on in the long term is implementing a different OAuth implementation that allows us more granular control in terms of
Which identity providers you accept?
well, like don't allow all Orchid users, but allow this explicit set of users.
Okay.
Just like, for
Cool.
example, Mitchell, I know you, I know you're an actual user. That still doesn't allow me to sort of allow the entire Jupyter Hub West to be
Right.
Orchid allowing. But for example, let's say you want to use Jupyter Hub and your folks, your group want to use Jupyter Hub. We can easily work together and we can deploy a Jupyter Hub deployment, a special one that is not different from the West one. That is just tailored for your use case that allows
Okay.
your
Got
login.
it. Perfect. Thank you.
People that were having issues getting into our matrix channel, Dima was scrubbing the database, so it was down for a little bit. It appears to be back up.
All right. Yeah, so Matrix might still be slow or you might experience connection issues. But we're also always available on support at nationalresearchplatform.org. I added it in the notebook if anybody wants a reference. And I hope everyone can see my screen now, as I was saying. So this is the main repository. And like I said, so we created this directory here called ESnet SmartNIC. Inside of it, sorry, this is from cloning the repo, which is, let me just start off from scratch. I'm just going to remove the entire directory. So inside of this directory that I created, I cloned the repo. And sorry, I need to also clone the tutorial repository. My bad. All right, here we go. So you have to clone the tutorial repository. You'll see the directory here. And we have the assets folder and the 3 notebooks and the set of slides. And after you clone the ESnet SmartNIC-HW repository, as we said, this is the hardware repository. This one has all the, like we said, there's a development environment and a deployment environment. This one has everything for the development environment. So you can write and test and start building and synthesizing your P4 logic from this repository. And like I said, this is the checkout we check out at, just so everything is working. This is the one we've tested. This is the one that we provide the appropriate Vivado version for, the appropriate other repositories for, and we do the steps in we do the updates in steps. So whenever we update our docs to a more recent commit, we do it for all components of the stack, so nothing breaks. And inside of the repo, you can see here, this is ls. So this is the directories you can see here. There's a directory called examples. Inside of examples, there's an example called P4 only. So inside of that P4 only example, let me show you here. Examples. So all of those are they're different examples that are trying to show the same thing in different fashions, different languages. For example, the P4 and Verilog one has 2 applications that are on the SmartNIC. One is written in P4, one is written in Verilog. We're going to be focusing on the P4 section here because Verilog is another topic to get into. But our P4 only is the simplest example to go through. And inside that directory, you can see you have a make file. So once you're inside the directory, if you run make, this will compile the example. This will do all the steps until you have a zip file that has all the artifacts you need to load it onto the FPGA in the subsequent notebooks. But you can see here, you can check out the details on your own, but the one we care about is the board variable. Setting the board, it's by default sets to AU280, which means it builds for the U280 FPGA and the AU280 board. And in our case, on Nautilus, we want to switch to AU55C, which is what we do in the notebook. And as you can see here, another thing is that inside of the P4 directory, we have another makefile and we have a sim directory, which is short for simulation. Inside of the sim directory, we also have test cases. We have another makefile, and this is for testing use cases against PCAP files and creating our own use cases with different table entries. So what we're going to be doing here is, this is my, going back to the examples, P4 only, P4. This is P4 underscore only dot P4. This is my packet processing logic, this file right here. This is the main file I care about changing. And for the sake of our example, we're not going to be copying P4 only and calling it something else. We're just going to be modifying this code. So as you can see, it's very similar to C and C++. I'm just going to be walking you through it very quickly. You can see here we're including two P4 header files like you do normally. And with like C and C++, we're including other P4 files the same way you include the header files in other languages. And we're defining, so the first step is defining the headers. You can see here, our logic defines what the Ethernet header is, which is 48 bits of the destination MAC address, the 48 bits of the source address, and 16 bits of the ether type. And in this logic, my FPGA as a SmartNIC, it's going to be expecting Ethernet packets, because you can see here in my header struct, I'm defining Ethernet. In my parser, I'm extracting Ethernet. So I'm extracting the Ethernet header, and that is what I'm parsing. That is what I'm performing actions and table lookups and whatever my logic is doing, it's getting performed on Ethernet. So my SmartNIC is expecting Ethernet packets. It's not gonna look beyond that. You can see it here. My logic only defines Ethernet. At that point, it's treated as if Ethernet is the packets and everything else is the payload. And one thing to note here is that there's no sort of sanity check on top of that. You're writing your own logic, and in many cases you're gonna have FPGA to FPGA experiments, which means if you misdefine Ethernet and you mess up what the bits are, for example, you define the MAC addresses as 32 bits instead of 48. Nothing at any other level between the FPGAs, if you're not including other network components, nothing is going to check you, nothing is going to drop packets, nothing is going to say, oh, this is a malformed packet or something is wrong. You're defining your own logic, and that is a double-edged sword. You can define your own packets, your own protocols, your own encapsulations, and it could be 100% arbitrary. And on the other hand, you can, if you're working with actual standards and RFCs, you can mess things up if you're not very careful. And this is my metadata that is populated by the SmartNIC when the packets arrive at the SmartNIC. And this is my parser pipeline. So my parser only parses Ethernet and then transitions to accept the packet. You can see here very clearly, then I go to the match action implementation block, and I'm not going to get into P4 much, but basically what this example does is that it does a very simple a table lookup. But with the result of that table lookup, it's looking at tables, and you can see, for example, in the sim folder test-forward-p0, this is one test case, and you can see we have packets underscore in.user, and this is defining test packets for my test case, and it's defining them as a hex dump. So whatever is preceded by the percentage, that is a comment, that is irrelevant. And the packets are defined as a hex dump. If I were to remove this file and put a pcap file instead, so it would be packets underscore in.pcap, everything will work just fine, and the output will be a pcap file. In this case, the output will be a similar hex dump file. And the accompanying metadata for my test case, because here there's no actual metadata, I'm testing behaviorally against the pcap file, I can explicitly define what the metadata is by hand in this file, and it's semicolon delimited, so every packet is defined by the one semicolon, and I can specify what fields to include and what fields to not include. For example, for the second packet, I can do something like this, and it would default the SmartNIC metadata fields to 0. And basically here what I'm doing is it's doing a simple table lookup for the Ethernet destination address, but on the result of this lookup, it is never dropping a packet. So even though it performs a table lookup, but essentially you can remove this entire block with the table and the actions, and no packets would get dropped. Because here's how my logic works. So everything is in the apply block. You can see in the apply block, I'm checking the metadata for errors. If there's a parsing error with the packet, at that point it gets dropped. Just if there's an error in parsing the packet. If it's a valid Ethernet packet, this is valid, checks if the Ethernet header is valid as I defined it. As we said, this is you defining what Ethernet means. And there's set valid that sets it to be valid. Here it checks if it's valid, it modifies SmartNIC metadata fields, and it applies the table. And if it's not valid, it drops it. So if it's not a valid Ethernet packet, it drops it. And I can't stress this enough. What we mean by valid Ethernet here is what we're defining to be Ethernet. And of course, if Ethernet is valid on the deparser, the last step before it egresses the packet, it emits it. What it emits as in re-encapsulates the packet. So the payload has the Ethernet the Ethernet encapsulation header that I performed the logic in. It only emits when it's set to be valid. So for example, when you have cases where you have IPv4 and IPv6 defined as headers, and you have packet.emit header.ethernet and header.IPv4 and header.IPv6, that doesn't mean you're screwing things up by emitting both. That means it is going to emit whatever is valid and only whatever is valid. And like we've mentioned, this is a very simple example. And if folks are interested, we can dive more into P4 and different tutorials. But what I want to show here is this in the assets folder here. We have a P4. Here it is. So we have another P4 underscore only.P4 file that we're providing, and I'm just going to walk you through what we've changed. So one thing is we introduced IPv4. Also, we're defining what the IPv4 header is, and we added it to the struct headers. This is universal among all P4 programs that you're going to be writing for the FPGAs. And you can see we're extracting header. Then in the ether type of the header packet, we're checking what the ether type is. If the ether type is the appropriate one for IPv4, we're extracting the header. Otherwise, we're just parsing the packet without looking at the IPv4. And similarly, in the apply block, we're looking if this is very simple logic here. We're looking if header.IPv4 is valid. That means if it is an IPv4 packet and everything so far is good, we have the ether type set for IPv4 and everything is valid. If the TTL is a field in IPv4, which is short for time to live. So whenever time to live hits 1, that means the packet is not supposed to make another hop. It should be dropped. So whenever we have a TTL of 1, the packet should be dropped, and TTL in other cases should be decremented. So time to live means how many hops the packet still has in its lifespan before it is dropped. And this is, of course, a safeguard. So packets are not hopping across the network in closed loops forever. We decrement for all IPv4 packets. If it hits 1, we drop it. The rest of the logic is the same. And like we said, we have packet.emit header.IPv4. That is not adding IPv4 encapsulation for everything. That is, if IPv4 is valid, this encapsulation is also added. And yeah, so we copied this P4 logic to sit in my directory. So in examples, P4 only. Our cell copies it. So this is the actual code we have now. Now, two key main things to note here is that whenever you're running Vivado or Vitus or whatever Xilinx tools you're running, you have to source a bash script that points to the actual libraries and commands and everything that is needed. So whenever you run and it gives you something like Vivado command not found, Vitus command not found, so on and so forth, make sure you're always sourcing the correct version. And Let me show you. Sorry. So this, if you see here, you have ls /tools /Xilinx. So this is mounted from a storage pool. So we use storage pools for all of our persistent storage, and this is directly mounted into every pod that users start, and it provides you with all the software stack that you're going to be needing. And of course, it mounts it as read-only, so users can use the tools, but of course, no one can mess it up for the rest and so on. And you can always check whatever versions of Vivado you have using tools, Xilinx, Vivado. With LS, you can see we're providing 3 versions. We're constantly changing things whenever users want to use a specific version because we aspire to provide the software, not only the hardware. If you're using a specific version, we can all and would like to add it to Nautilus, just hit us up, communicate that with us on Matrix, and we're always more than happy to add it. For this specific commit that we're using 2023.1. And like I said, this is the licensing server that we're pointing to with the Xilinx d_license_file environment variable. So when I run these 2 lines, I should be able to run Vivado and everything. For this case, I'm running it for the simulation, so I'm changing the directory into the sim directory. And I'm just printing the few lines from packets_in.user. As we said, this is a hex dump of packets. And so for example, you can see here, this is packet 1 right here. And of course, I think it's also semicolon delimited. So this is 1 packet, everything with percentage is ignored. And we're going to be creating another test case so we don't mess up this original one. And we're going to be calling it test-forward-p1. And we're adding it to the make file. So this is the make file for the simulation. You can see here we're changing P4 and BM, which is a behavioral model, directories to P0 and P1 to include it. This is another thing you have to do if you're creating use cases. If I look at my environment variables, just making sure it's correctly pointed. And if you run into licensing issues and would like to check it, like we said, we're on Coder. In Coder, you have a no VNC button. If you click on it, it'll show you your desktop environment. There you can open a terminal, you can run the same source command and just type in VLM. So that would be just VLM, which is short for Vivado License Manager. It will show you the license manager and you can see if the license server is working or not. Now we're inside the simulation. We want to run this make file, so we're gonna run it and directly look inside the test case folder, the test case we just created. So you can see that it is running the commands, and this is what we have now. So I'm just gonna show you very briefly. So these are table entries. These are my control plane table entries. So whatever table lookup I actually do on the packets, I have to provide in a file called cli_commands.txt for each test case, of course. And the CLI, you can see here, this is the output from actually adding the table entries. So if one of them was malformed, you can see it in this file. It's sort of a log. And underscore model, you can see here how the model is processing the logic. So you can see action entry and how the control plane table entries are handled. And of course, I'm not gonna waste your time on table entries and control plane, but as I mentioned before, if folks are interested in P4, we can post a more in-depth P4 tutorial. And I'm just going to be showing you. So this is my packets in. And this is the head. This is showing my packets going in. This is showing my packets coming out as a hex dump. What I'm going to do now is I'm going to use the Scapy, which is a Python library that allows you to generate PCAP files. And I'm just going to be generating a very simple PCAP file. It's going to be placed in the packets in this directory as packets in.pcap. Essentially, what it's providing is just an Ethernet IPv4 packet that has TTLs from 1 to 10, just to test our behavior with our P4 that we're writing. And once it runs, you can see we have our PCAP file here. And we're removing the user one. We're removing this one because we don't want it to collide. We want it to use this file for our use case. Of course, we could have generated a user file which has a hex dump, but PCAP files essentially are more easier to look at, especially when you have tools like T-Sharp, which allows you to look at PCAP files, which is what we're doing here. So this is our packets in. This is our IPv4 packets. As you can see, the addresses, the packets is just very exemplary. It's not very resemblant of actual network data, but it's just to demonstrate our logic. And when we run make, since we're in the sim directory, it'll run our simulation. And you can see here. So we have our packets in. This is our packets in. And the second command, I'm specifying the field ip.ttl. So this is my packets in. Before going into the simulation, I'm printing the time to live, which is from 1 to 10. My packets out, I'm doing the exact same thing. But when it's printing 9 packets. And I know it's a little tricky to see here because they all have the IP addresses. I could have used more variety to actually highlight what has gone here. But what happened here is this first packet, since it's at TTL1, it got dropped. That's the one that dropped. And the one with TTL2, it decremented. So it became 1 and so on and so forth. So this is the logic that we've wanted. As we said, this is our metadata going in. And this is our metadata going out. And you can see here, since our P4 logic specified RS entropy and so on, we have more metadata going out. Our metadata is explicitly listed going out, but going in, you only define what you want to change. The other is defaulted to 0. And this is essentially how you run behavioral tests against PCAP files. I'm just going to be very quickly showing you before we stop for questions. I'm just going to be very quickly showing you how to build this actual logic. So it's in the second notebook, which is much more straightforward to run. You go into the P4 only directory, so the root directory of the example you're running in. And you can see there is a make file. Like we mentioned, you have to explicitly set the board. This is a set command that replaces this comment with this. So it sets the board to be AU55C like this. And from here, since we're sourcing and exporting like we did before, from here we can run make. And I'm just going to run it. It's not going to run in time. I'm just going to show you what happens when you run make. And the reason it was commented out because so this does everything from taking the P4 into all levels of and stages from synthesis and hard design implementation and so on and so forth into packaging it into a zip file. And on average, this takes roughly 5 hours to run. So, I don't want to hold you for 5 hours watching it run. And I also don't want you to rely on Jupyter to run, with no friction for 5 hours. So there's various ways to run the make command. And as long as you're carrying out these steps, you're sourcing Vivado, pointing to the environment variable, and you're in the right directory, you can run make from multiple ways using the Jupyter notebook, using the bash terminal, for example. You can, from Coder, use its terminal, use VS Code. Coder also has a CLI tool that is installed locally on your machine. You can use it to SSH into the pod you're in. But you can use the kubectl exec command. So this allows you to exec, which means run commands into whatever Kubernetes pod you own. And this is highlighted in red because this goes through the Kubernetes API. This is very slow and very unreliable, and it also makes things slow for all cluster users. But the ideal way to run it, at least for me, this is what I recommend, is running inside an OVNC. Because inside an OVNC, you can have your GUI terminal. When that runs, your computer crashes, whatever happens, that NoVNC session, as long as the pod is running, is persistent. And you can always click that NoVNC button and you'll watch your same terminal. And on the other hand, you can also use tmux and screen and so on and so forth. But the result of running this will be a zip file inside of artifacts. So we're in the hardware repository. There's examples, P4 underscore only. Inside P4, you'll see here there's a new folder that will be created once this is done. It'll be called artifacts. And inside of it, you'll see your program, just P4 underscore only. Inside of it, you'll see your zip file, which is used in the third notebook that we have, and that zip file. And we provide you here with an example that can be directly downloaded if you want to test things out without actually having to wait the 5 hours. If you just want to test how the deployment framework works, this is a publicly available artifacts file that we provide for the simple packet forwarding logic. So whatever packets go in with ingress, they come out with egress. And we go through all this to show you all the steps of running all the tools and SmartNIC tools on the FPGA. And of course, all those steps can be carried out in whatever environment you're running in, whether it's NRP, whether you're running the fabric testbed, and so on and so forth. And I'm just going to stop here for questions.
I think a lot of people got added to Coder. I'm not sure if how many were successful at launching. Um, it,
Has anybody ran into any issues? One thing, so if your pod is not starting, there's for example 20 of us on the call. If we're all, for example, trying Node-2-11 and we're all, for example, requesting 32 CPU cores, it's bound to run out and then your pods won't land. But for example, you up to this point, you can try it on whatever node is available on this template or the U55C template.
I'd like to ask everybody to send us a message, email or in Matrix or Slack, whatever choice, and let us know what issues you did have, and we'll work with you to solve those. I know some folks were still getting the blocked from even logging in, so that might be a SSO issue that we have to dig into.
Oh. So is anybody trying to access now and not
Yeah, I was sorry. I was trying to log in, and I just had a very weird issue saying no email found. I'll try to clear my cache and log in again later. Yeah, I'll keep in touch on Matrix.
Yeah, that'd be great. Send us a message on Matrix, and we'll make sure that I might have missed somebody trying to add folks. It was quite a few.
Is it the same? Sorry, I'm gonna do something real quick. I'm just gonna stop sharing for a second. All right, so I'm just gonna disable the lock on signups temporarily. And users will be able to land. It'll take a So it'll take a minute to start. You might notice the coder website might not work for a minute while it restarts, but when it does, all of you will be able to sign up. I'm just gonna ask, so far, was this very fast paced in terms of providing coder, or were users able to follow along with the material? So the reason I asked, so we have the recording in case this was somewhat fast paced and we have the coder issue. You can always rewatch the recording and follow the notebooks step by step to redo everything on your own. But we always have the option of whoever's running into issues, first of all, feel free to always reach out, and uh, I'm always more than happy to sit on a Zoom call one-on-one and work out whatever issues you're facing. And also, I realize 1 hour is not a lot of time. We didn't get to cover much. I was hoping we can actually cover loading the actual logic on the FPGA and carrying out more meaningful experiments. So I'm gonna be sending the email to everybody with the recording in it and asking you for whatever input you have. Please feel free to be as brutally honest as you can. This is, at least for me, this is my first tutorial of this nature of actually having everything hands-on on Zoom. And I realize there's many components to cover, but going forward, I would like to improve from here on. So whatever input you have, please don't hesitate in providing us with your input. But uh, I just want to reiterate, if anybody has any questions, I don't want to be,
Yeah,
leaving.
can I ask a question?
Yeah, go ahead.
Okay, so in the P4 code, we were using the XSA architecture, isn't right? Correct.
Yeah.
So, okay, so this architecture is specifically for the Xilinx for this board, or will it allow us also to write P4 codes for other boards?
So you can write, as far as I know, and as far as I tested, you can write P4 code for all Alveo cards that support the OpenNIC shell. We're using the same XSA architecture without issues whatsoever. It is going to be different from writing P4 for Tofino architecture and Tofino 2 and so on. In terms of, there is some limitations and some stuff like, if I remember, and
Yeah, as far as I know, it's more similar to the BMV2 model in terms of syntax and so on, but it is definitely mapping everything to Vivado, and the architecture of FPGA boards and Xilinx products. For example, if we look at Acronix or we look at Intel FPGA SmartNICs, that is not gonna work. And I also wanted to ask you, the tool you are using to convert from P4 to whatever binary files you need to load on the FPGA board, is it like a Vitis networking P4?
yeah, and the use of Vitis, not P4, is the exact use case of why we need a licensing server, and we need to always renew our evaluation license. Because we're using IPs for Vitis, not P4. When you might see it listed as SDNet in the license manager, and that is one main use case for why we push users to use Coder, because you're already pointing at the license server because you are gonna need it to compile or to synthesize.
Okay, I see. Okay, thank you.
You're welcome. And so the simulation you saw against the PCAP file, this is BMV2 with the constraints of using the uh, Xilinx compliant P4. So and so far in all the test cases we've tested, there's been very little difference in actually running against PCAP files with the behavioral simulation and running on actual hardware. If normally when it compiles here, it compiles here, except for very, very specific edge cases that you are very unlikely to run into. And of course, so for I realize there's some users here that are active Fabric testbed users. You can use the same software stack to compile for the U280s and take that software stack and run it on the U280s on Fabric. And also in Notebook 3, you'll see we provide you with the direct container registry for the SmartNIC DPDK Docker container and the Xilinx Lab Tools Docker container that the stack relies on. This is a public registry. So for whoever is also testing on Fabric, you can pull the same containers from the same registry instead of building them or attaching a volume to your Fabric experiment as well. Any more questions? I'm just gonna check chat too.
So yeah, let us know, send us an email as a response to Mohammed's message with the recording, with any issues or suggestions, and definitely come back anytime and chat with us. You should all be able to log in. I know there's a couple that couldn't, but we'll walk you through. We have a coder channel in our Matrix service that you can jump into there and talk to other coder users also.
All right, I'll just send my email and the email for our support ticketing system. And if anybody has any inquiries and Matrix is down, you'll reach us whether here or there. Matrix should not be down.
Matrix is back up already.
Perfect, perfect. Like John mentioned, I'll reach out to everybody with an email, and thank you all for attending. I realize 1 hour is not enough time, and I've already ran overtime, but hopefully we can schedule a future session as well to go over loading on the actual FPGAs and carrying out experiments and showing you more meaningful P4 workloads.
Thanks, everybody.
All right, thank you all.